Hello and thank you for watching. In this video we're going to cover continuity. So first of all, you may be used to the definition of continuity being that, okay, if we have a graph and we can draw our function without taking our pencil off the page, then it's continuous. But this is not entirely true, and I'll get on to why soon. Say we have a function mapping from reals to reals, for example. Then we say that f is continuous at x0, at some point x0, if, and then we have three conditions. So firstly, we want f of x0 to exists. We want the limit as x goes to x0 of f of x equal to, or exists. We want this to exist as well. And then the last condition is that we want the limit as x goes to x0 of f of x equal to x0, and all this information can just be summarized by this last point. So it's continuous at x0 if the limit as x goes to x0 of f of x, is equal to the value of the function at x0, because this requires f of x0 to exist, it requires the limit to exist, and it requires the two to be equal. Okay, so for example, say we want to see that x squared is continuous at 0. For example, if we have some graph here, intuitively we can see that the limit exists at 0. There's like nothing in the way, there's no jump discontinuity, there's nothing here. X squared at 0 is just 0 squared, which is 0, so it's going to be continuous at 0 intuitively. Now we say that this function f, a function f, is continuous if it's continuous, it is continuous at every point of its domain. So, right, this seems like an obvious definition, and I guess it is quite an obvious definition, but this is why our school definition of continuous breaks. We said that if a function can be drawn without taking our pencil off the page, it is continuous. But the reason why this is entirely true is because let's consider f of x equals 1 over x. So this is a function mapping from the reals without 0, because it's not defined at 0, to the reals themselves. So maybe you can already see where this is going, but if we draw 1 over x, we have this here, and we have this here. Now it might be tempting to say, okay, our f of x, our 1 over x must be, can't be continuous because we have this gap here. However, we said that it has to be continuous at every point of its domain. So this domain does not include 0, and so our 1 over x is actually continuous despite this discontinuity at x equals 0. Okay, so now I'll give a quick example of how we can show if something's continuous, or rather I'll explain rigorously what it means for a function to be continuous. we saw before that we need our condition of the limit as x goes to x naught of x, or f of x, be equal to f of x naught. Now, from our previous videos, we looked at a lot at limits already, and this is true if we have that for epsilon greater than 0, we have the modulus of x minus x naught being less than delta, implying that our f of x minus f of x naught is less than epsilon. This is the same thing as we've been doing this whole time, where our a from before and our L from before is now just x naught and f of x naught. So to give an example, let's say we have the limit as x goes to x naught of x squared. So this way we're proving for a general point, so this way we're proving for continuity. And okay, what do we want this to be equal to? We want it to be equal to x naught squared, because this is what we get when we plug in x naught into our function. So we're attempting to prove this now, and it follows like every other proof we've done. So okay, say that we have some x minus x naught less than delta, and we want to get from this to x squared minus x naught squared being less than epsilon. So from this we can see, oh okay, we have difference of two squares, which gives us this. Okay, so now we're thinking, well, these are the same, aren't they? So we're only missing this essentially. So what we want to do is, okay, say our delta is 1 or less than 1 in this example, then we know that x minus x naught is also less than. And we can do this because if our epsilon is very, very small, our delta will also be very, very small. So under this assumption that it's less than 1, delta is still going to be less than 1. However, if our epsilon is large, then if we choose a small delta, then we'll still be within the range that we want. Okay. So if we have this, we have that x minus x naught is less than 1, and it's between minus 1 and 1. So now we can say that, okay, we have 2x naught minus 1 being less than x plus x naught being less than 1 plus 2x naught. So now we're thinking, okay, we can just take the modulus and everything will be fine. However, we need to consider that our x naught might be negative, so we can just we can make up for this by saying that, okay, this is also going to be less than the modulus of 1 plus 2 times the modulus of x naught, because this is either going to be greater or equal to x naught. If it's negative, it's going to be greater. If it's positive, then it's going to be equal. And so now we can say that our x plus x, the modulus of x plus x naught is going to be less than 1 plus 2 times the modulus of x naught. So now we're thinking, nice, we found what we want, so we'll choose that our epsilon is the minimum between 1 and 1 over 1 plus 2x naught. And again, as a reminder, this is because we made the assumption that our x minus x naught is less than 1. So if it's less than 1, we have this. If it's not, we can just set it as 1. Okay, so now the proof, the proper proof. Suppose that epsilon is greater than 0, then we have x minus x naught being less than, and then we have this, so we'll say oh, sorry, this is supposed to be a delta here. Then we have this being less than epsilon over 1 plus 2 times the modulus of x naught. And so multiplying by the modulus of x plus x naught, we get that this is less than epsilon over 1 plus 2 times the modulus of x naught times 1 plus 2 times the modulus of x naught. And therefore we get that x minus x squared minus x naught squared is less than epsilon, and so hence x squared is continuous. Alright, now I'm going to give the viewer a few exercises to finish off the video. So we have our first exercise, which is prove x cubed is continuous. Second one, a little bit harder. We'll have that prove that 1 over x is continuous. A little bit harder again, so I'll add another star for 3. Prove that x to the n, where n is a natural number, is continuous. And finally, as a triple challenge, we'll have that prove x to the 1 over n, where n is a natural number, is continuous. Okay, thank you for watching. Hopefully this video helped you understand continuity formally. That's all, thanks for watching, bye bye.